With this example D1, we now move on to a 4 random variable problem, which we will solve with FORM. We continue with the same problem setup that we used in problem groups B and C, that there's a cable in tension, but there is an important twist here as well. So let's first read this, and then we will talk about that twist. Okay, so as you see, we have added a 4th random variable, a dead load, in addition to the yield strength of the cable, the cross-sectional area of the cable, the live load Q, and a dead load D, the 4th one, the new one now. Y, A, and Q, they are distributed as before. D is normal, but importantly, and that is the twist, D and Q are dependent. And the dependence information is not complete. We have been given partial information, and which is actually quite typical, is in addition to knowing the marginal distributions, we know the correlation coefficient. The joint density is not available. So we just are not able to employ, for example, the Rosenblatt transformation, which would be possible if we knew the complete dependent structure. But we have knowledge of the correlation coefficient rho between D and Q. So obviously, if we have to take that into account, one of the clear options is the Netapp transformation, which is what has been recommended in this problem statement. So let us tackle this. These are the 4 random variables, x1, x2, x3, and x4. The limit state now is x1, x2 minus x3 minus x4. Now, how do we do the transformation? For the independent random variables, there is not any difference really from what we did in the previous example C1 when they were all independent. So let f be the CDF of x, so I going from 1 to 4. Now how do we transform for 1 and 2, which is yield and area? We'll just do the full distribution transformation as we did before. Nothing has changed. So you can go back to those steps and see how we did that for x1 and x2. Things become different and interesting for x3 and x4. And let us take that up. So for x3 and x4, this is the correlation coefficient, rho dq, and this is the correlation matrix. So 1 in the diagonals and rho dq in the off-diagonal positions. So as we discussed when we were discussing Netapp transformation earlier in the previous lecture, we find the Cholesky factor C of R, so that CC transpose is equal to R being the correlation matrix of D and Q, or x3 and x4. Now we define dependent standard normal variables in terms of the independent standard normals. So x3 goes to y3 goes to u3, x4 goes to y4 goes to u4. So you remember that map. So let's talk about the second and the third in this sequence. So y3 and y4 are given in terms of a linear combination of u3 and u4. And because the way we have defined C, obviously even though the u's are independent, y3 and y4 have a correlation coefficient of R. That is what we intended to do, so we have achieved that. Now let us employ the full distribution transformation between the y's and x's, and thereby we are imposing the dependence between x3 and x4 as well. This is how we transform y3 to x3 and y4 to x4. And just for closing the loop, u3 is a linear combination of the y's, and u4 is another linear combination of the y's. So this would let us express the x's, the x3 and x4, in terms of u3 and u4, and because the way we have defined y3 and y4, x3 and x4 would be correlated. There's one subtle point here, is that the correlation coefficient between x3 and x4 achieved this way would probably be slightly different from rho dq because of the nonlinear transformations involved between y and x. In most cases this is small enough, but if we want to be very accurate, then we would need to do an iterative solution to pick the exact value of rho dq in finding C, the matrix C, so that we are able to impose the exact rho dq between x3 and x4. We are now ready to set up the optimization problem. And as we did for C1, example C1, we will stay confined to the x space. So our decision variables would be x1, x2, x3, and x4. But we have to minimize the distance in U space. So the way we achieve that is define an objective function R in terms of the square of the U's. And the constraint is of an equality type that g of x1, x2, x3, x4 is equal to 0, which is x1, x2 minus x3 minus x4 equals 0. And we need to be able to express the u's in terms of the x's. So we have been doing this in the in the previous two slides. So let's just put everything together. u1 is related to x1 through the full distribution transformation, which you see on the screen. Phi of u1 is the f of the yield strength, which is the Weibull form. For u2 and x2, it's simple normal to normal transformation. And then for x3 and x4 to u3 and u4, we need to linearly combine them after doing a nonlinear transformation, which we just saw in the previous slide. So putting all of that together, u3 is C11 inverse of the distributional transformation with x3 plus C12 inverse with the distribution transformation of x4. x4 being normal, you see the simple x4 minus mu d over sigma d form there. Likewise, for u4, we express in terms of x3 and x4 the same way with coefficients C21 inverse and C22 inverse. So the problem setup is now complete. We have an objective function R, as you see on the top of your screen. The constraint is given just below that, and now the hidden relation between the x's and the u's are all stated in the box below. The solution is the square root of the optimum R star, and the design point, if we want, would be the output of the optimization exercise.